Everyone, today we're looking at the electrostatic repulsion or attraction force that we've been seeing in the labs. And we started off with this video where we had two charged objects that were the same charge brought towards each other, and you can see that they eventually start to repel. And we can measure that repulsion and graph out the amount of force that the object felt versus the distance of separation between the two objects. And we did end up seeing this curve where the force was very strong when the charges were close to each other, and the force was very weak the further they got away. It is an inverse relationship, and according to the person that studied this, Coulomb, this is an inverse squared relationship. So what Coulomb's law states is that the electrostatic force between two charges is proportional to each of the charges and inversely proportional to the distance of separation squared. So it looks very similar to what we did in gravity, where we had the big gravitation constant, mass 1, mass 2 over r squared. This time we're dealing with two charges and the distance between the two charges squared again. Constant this time is now this 1 over 4 pi epsilon 0, where epsilon 0 is known as our permittivity constant. It's 8.55 times 10 to the negative 12th Coulomb squared per Newton meter squared. So what the permittivity constant tells us is the ability for the empty space to allow a electric force to propagate. If you take 1 divided by 4 pi epsilon 0, you end up with Coulomb's constant, which is 8.99 times 10 to the 9th Newtons meter squared per Coulomb squared. So it's a lot stronger than gravity. The electrostatic force is very strong compared to the gravitational force. Remember, the G constant was to the negative 11th, while now our K constant here is going to be to the positive 9th. So we get a lot of force from a very, very small amount of charge. So if we wanted to calculate this, let's figure out the force between an electron and the proton in a hydrogen atom. So the hydrogen atom is the simplest of all the atoms. It's got one proton and one electron that's orbiting. And since they are a positive and a negative, they're equally and oppositely charged. So if I'm looking at my Coulomb force, in this case, both of my charges are the same, 1.6 to the negative 19th. The distance between them is 5.3 to the negative 11th. So I'm going to put those values into my equation, and remember that the Coulomb constant here is 8.99 times 10 to the 9th Newtons meters squared per Coulomb squared. So plugging in all your values, you should get a force of around 8.21 times 10 to the negative 8th newtons. And make sure that all your units do cancel out here. Remember, a Coulomb times a Coulomb will be a Coulomb squared on top. An r squared on the bottom would be meters, and we square that. And you're going to multiply by our Coulomb constant, which is the meter squared disappearing and the Coulomb squared going away, leaving us newtons of force. These two objects are pulling on each other with about 0.8 nanonewtons of force. You think, well, that's not a lot of force at all. But we're dealing with very, very small objects here. We're dealing with an electron and we're dealing with a proton. The force may be very, very small, but if I wanted to solve for the acceleration of, say, the electron, I'd have to divide that force by the mass of an electron. Go back to your constant sheet that is given to you for any AP exam, and you'll find out that the mass of an electron is 9.11 to the negative 31st, so it's a very, very small mass. And if you divide by the mass of an electron, you'll find out that an electron is accelerating around the proton at 9.106 10 to the 22 meters per second squared, which is a huge acceleration, much more than the acceleration due to gravity. But how can that poor little electron handle that? Well, it's an electron. It has a very small mass, and it's an inanimate object. So that's an example of how you use Coulomb's equation. It's very similar to gravity, but now we're putting charges in instead of masses. But when you have more than two charges present, we have to use something known as superposition to find the total force. And this is why I told you in class that when we write the Coulomb equation, I suggest you write it like this. The electrostatic force between two objects is going to be K times the absolute value of charge 1 times the absolute value of charge 2 all over the distance of separation squared. So when you have that equation there, no matter what sign they tell you of the charges down below, I want you to get a positive amount of force. And then, to figure out what direction that force is pointing, that's when you look at your picture and you figure out which way things are going to go. So in this problem right here, we've got three charges. We've got Q1, Q2, and Q0. So if I want to look at the interaction of charge 1 with the other charges here, charge 2 is going to attract it forward. So it's going to want to move to the right. Charge 0, on the other hand, is positive. So charge 0 is going to want to repel it to the left. So when you look at that, depending on the values, when you put in your charges into the Coulomb force equation, those forces may cancel out. And charge 1 may feel no force at all if both forces are equal and opposite. If they're not equal and opposite, then the object will feel more force in one direction. And we'll know that by finding the vector addition there, or in this case, vector subtraction. Let's look at Q2. Q2 is going to be attracted to Q1 with an equal and opposite force that we calculated already, and it'll be attracted to charge 0 there. Now again, if those two forces on charge 2 are equal and opposite, then we will actually see that charge not move. But we're going to put in our values and see what the total force is to see if things are balanced or unbalanced. Let's look at charge 0. Charge 0 is attracted to charge 2 with an equal and opposite force, but it's also being repelled by charge 1 in the opposite direction. So again, put in your values and see what the total force is. Put the absolute values of these charges in there, and if you look, each of my charges are 25 or 10 or 20 n coulombs, which means nano. So really, when you put that into your calculator, you want to put 10 times 10 to the negative 9th coulombs. Or if you know the shorthand on how to do that with your calculator, you're going to save yourself a lot of time. That's how you want to use Coulomb's equation when we have more than two charges. What if we had 4 charges? Well, no surprise there. We're going to find the force of charge 1 on charge 4, charge 3 on charge 1, and charge 2 on charge 1. Adding all those forces together will give us the net total force on an object. So we are back to worrying about vectors, worrying about directions for all the forces, and breaking angled forces into components. So you're going to need the direction and magnitude of each of those vectors. So like this is trying to show us here, you've got 3 charges in this triangular shape. You can see that charge 0 up at the top there feels attraction to the negative and repulsion from the positive. So the net force is down and to the right. Let's do our own example and see if we can crunch out some numbers too. So here's our example. We've got charges that are in this xy plane here, some positive, some negative, and we want to find the total force on each object. So object 1 is repelling object 2, is also attracting to object 3, and you can see I've drawn the forces for the other charges as well. If I'm interested on the net force on charge 1, I need to find the force of 1 from 3 and the force on 1 from 2. So I have to use Coulomb's force to get those two forces there. So do that work now and check back with your answer. Crunching out your work, you can see that 1 is repelling 2 with a 5.05 to the negative 7th newtons, and you can see 1 is attracting 3 with a 3.37 to the negative 7th newtons as well. So if I want to find the total force down there on charge 1, the 1 on 3 force is to the right. The 1 on 2 force is the one I have to break up into components because it's at an angle. So I need to find its x and y components, which means now I've got to figure out the angle that it's being repelled at. Well, just using some trigonometry here, I can see that I'm 2 over and 2 up from my charge, which means that I must be at a 45-degree angle, and that also gives me a 45-degree angle down here. That'll be able to help me get my x and y components, and then what I'm going to do is subtract my x components and combine that with my leftover y component to find my total force. So here's your leftover forces here. Negative 2 times 10 to the negative 8th in the x direction, and negative 3.57 to the negative 7th in the y direction, meaning you have a force in the negative x and negative y now left over. So your net force must be down and to the left. So if I want to solve for that net force, you want to take both of those components, square and square root them, and you should end up with around 4.09 times 10 to the minus 8th newtons. And using your trig, you should get about 60.7 degrees in that down left direction. That's how you solve for forces with multiple charges in more than one dimension. But the last question they can ask you here is, what if you have two positive charges and say a negative in the middle there? Well, if I have two positive charges and one negative in the middle, that negative is going to be attracted to both. So if it's attracted to both, the question could be, what location between these two charges would the electric force balance out and equal 0? So what I'm asking you is, please make the force of 1 acting on 2 equal the force of 2 acting on 0. So when you try to set those two up, that means you're going to have K, Q1, Q2 over X distance apart. Don't forget to square. And for the second charge, you're going to have K, Q2, Q0 all over that total distance there. The total distance looks like it's around 3.5. So I'm going to say 3.5 minus X squared. In our equation here, we have the K constants equal on both sides. Charge 2 is the same on both sides. So we can cross those out, and you'll be left with that Q1 over X squared, which is the distance from charge 1 to the point where that middle charge feels no force. And on the other side, you have Q0 over 3.5 minus X, since they're 3.5 apart, and the leftover distance is that 3.5 minus X. Make sure you square it and solve for X. We can figure out exactly, just like we did for gravitational fields, where the gravitational field canceled out. We can find where electric force cancels out using the same principles.